let's start. Let me share the screen. Here it is. Okay, here it is. Can you see my screen? Good. Okay. So here it is. Now let's start. Let's start talking. Let's start presenting. And this is the last lecture that I told you regarding the physical oceanography instrumentation. And here is the satellite remote sensing. You remember that that we were talking last time about the other type of satellite, or the other type of remote sensing, but this time we will be talking about satellite remote sensing. And the satellite remote sensing is based on two principles, two applications. One is the passive application, which is the ocean color and sea surface temperature, where the satellite receives the signal from the Earth. We analyze then the signal. So the signal is transmitted from the Earth, or depending on temperature, or ocean color. Then we have the active applications. Active application means that the satellite sends the signal toward the Earth and then looks the reflecting signal from the Earth's surface. So these are the two essential principles of satellite remote sensing. And so we will now be discussing these things. Okay, just a minute. I will be back with you in a minute. Just a minute. So this is the introductory slide, and let's start looking at what we have here. Oh, sorry. So this remote sensing uses this is first of all, what is the remote sensing? The remote sensing is the art. It's not the science. I don't think it's science. It's science. It's application science, which is an art of obtaining information about an object, or area or phenomena, where the data acquired by a device are not necessarily in contact with the object. So this is remote sensing. So the satellite is far away, and the object is the Earth. So satellite remote sensing uses electromagnetic radiations to measure near-surface ocean properties. So we have, in order to do that, we have to look at different parts of the spectrum. So we have the visible part of the spectrum, between 40 and 1,000 nanometers. We have infrared, and we have microwave, passive and active. Visible, obviously, has been used for determining the sea surface color. If you remember, when we were talking about the possible indicators of the dense water formation, where we noticed the patch of the high chlorophyll concentration at the surface, this reflects to the color of the sea surface. So obviously, this application is in the visible part of the spectrum, because in the visible part of the spectrum we determine the color, and then we somehow use specifically developed algorithms which then are transforming these information on the color to the concentration of the phytoplankton or chlorophyll. Then we have the infrared measurements. These are the two are The two are passive. Infrared, where we obviously we are in the infrared part of the spectrum, where we measure the sea surface temperature. Then we have the microwave measurements, which are active and passive, which we will see later what kind of information we do obtain from these measurements. And the electromagnetic spectrum is like this one here, and the electromagnetic spectrum uses the proportionality between the temperature and the energy of that part of the specific part of the spectrum in order to obtain the temperature. So the temperature, the determination of the temperature from satellite, from remote sensing, is in fact based on the black body curve of the infrared radiation. So since we know black body curve, which is this one here, and this is extraterrestrial solar curve, so this is outside of the atmosphere. Then we, on the basis of these two things, and we can obtain the temperature. So we obtain the temperature using this relationship, and we calculate from the black body radiation. So that's the basic principle in which this base the sea surface temperature measurements. Obviously, if we doing the measurements, doing the satellite measurements, either type of satellite measurements, or invisible part of the spectrum, or the sea surface temperature measurements, and then what that means infrared radiation, we have to take into consideration the atmosphere. Why to consider consideration the atmosphere? Because the atmosphere really distort the signal which comes from the Earth's surface, because the atmosphere partly absorbs the electromagnetic radiation from the Earth's surface. So we have somehow always, all the time, when we do these measurements, in order to get the right values of the temperature or color, we have to introduce corrections due to the presence of the atmosphere. In some situation, you cannot really measure anything from the sea surface due to the presence of clouds. For example, if you do the sea surface temperature measurements, if the atmosphere is cloudy, you cannot do the sea surface temperature measurements, because the clouds are absorbing this infrared radiation. Therefore, you cannot measure the temperature. So the coverage of the sea surface temperature measurements is dictated, or is determined, or is conditioned by the presence of clouds. In order to get somehow the continuous time series of the sea surface temperature, because as you remember, I showed you the time series of the sea surface temperature. In order to obtain that, we have to combine various situations over the sea surface, with clouds, without clouds. We mask clouds, and then we do something like integral of all the available pictures, and then obtain the value, the sea surface temperature distribution over the Earth's surface. Here is the illustration of the passive and active satellite remote sensing. Here is the passive one. So you can see that what is happening is that the sun is transmitting the energy to the sea surface, to the Earth's surface, and then this energy, which is accumulated in the Earth, is then transmitted to the satellite. The satellite then measure this amount of energy, and using a specific algorithm, determines the sea surface temperature, whatever it is has been used, or the same thing is for chlorophyll. Active satellite remote sensing is based on the fact that the satellite sends the signal from Earth, sends the signal toward the Earth, and then looks at the reflected signal, and this does the differences between these two. For example, one of the measurements which are active is the sea surface temperature measurements. Sea level measurements, oceanic sea level measurements, where the satellite essentially sends the signal to the surface, and this reflects toward the satellite, and then we look at the time needed to the signal to pass from the Earth back to the satellite. So the difference is in the travel between the outgoing signal and the receiving signal distance between the satellite and the sea surface height. So this is, as I told you before, this is these differences between different parts of the Earth ocean is on the order of a centimeter. Therefore, the precision of these, the accuracy of these measurements should be on the order of centimeters or even better. And so this is how these passive and active satellite remote sensing are functioning. Then we have different satellite orbits. The satellite can be or in polar orbiting satellite, or can be geostationary satellite. Geostationary satellites are typically at the 36,000 kilometer altitude, and they are in a stationary position with respect to the Earth. Then we have a polar orbiting satellite, which are only 850 kilometer altitude above the sea surface, and they are going around the Earth, while this one is geostationary, so relatively steady with respect to the Earth. Here it is one example of the polar orbiting satellite. And you can see that it's doing this kind of orbit, and geostationary, on the other hand, is it's put so that it looks to the equator. So its satellite signal really cannot reach the polar areas. It gives a very good resolution in the equatorial up to mid-latitude areas. So it's a stationary really with respect to the axis of the rotation of the Earth. And geostationary, so there are a series of geostationary satellites which they have a different usage. One is the Meteosat, as the same names as the meteorological satellite. So there are a number of satellites which are now orbiting around the Earth. Then we have a near polar orbiting satellite, which is the satellite which measures the sea surface height, and this is the orbit of the satellite and the coverage of the Earth in this way. As you remember, I told you before, every 10 days there is a complete coverage of the Earth with the sea surface height measurements. Okay, so but we cannot do really the remote sensing measurements without having a ground truth, what we call the ground truth data. We cannot measure. We do have to have the ground truth data, which are in situ measurements, which are needed for validation of the remote sense data. Because, for example, if we are talking about the chlorophyll, yes, it is there is a algorithm which transforms the information on the sea surface color, to from the signal are received from the Earth to the sea surface color, but this has to be connected to the concentration of the phytoplankton, because the color is not directly transformable, cannot be transformed directly into the phytoplankton concentration. Therefore, we have to have the direct see-through data. And one of the examples where we have these measurements is here in front of the Venice Lagoon. It's Oceanographic platform, which does the continuous measurements of the sea surface phytoplankton concentration, and then this is used to validate the remotely sensed data. We can see also that the surface drifters are used to, so that means that not only the Eulerian measurements, so the measurements fixed at the Earth, the Lagrangian measurements, so the measurements which are obtained by following the currents, can be used to validation of the remotely sensed data. And one of these instruments or these platforms which have been used to these kind of measurements is surface drifter. Surface drifter, as we know, they apart from measuring or following currents and be used for surface currents, they also measure sea surface temperature. So these sea surface temperature data are used to validate the remotely sensed sea surface temperature data. And so after getting the image from the satellite, there is a whole series of analysis or of the figures which have to be transformed in a geo-based system. And you see, this is how the satellite image is obtained from the satellite. You can see that this is the Adriatic, and you can see this deformed because of the angle at which the satellite looks at the sea surface. Therefore, we have to adjust these different angles of where the satellite looks at the sea surface, at the Earth's surface. So this is what has been obtained directly from satellite. And here, these white patches, these are the clouds, and obviously you can see that below the clouds you cannot see what is going on in the sea surface. Once you do your adjustment for the angle at which the satellite looks at the sea surface, then the result is this thing here. This is the result of the final result of the analysis of this data. This is the ocean color. So the ocean colors, as you remember, what I told you, that the more blue the color is, the less concentration of the chlorophyll or anorganic material is present in the sea. And you can see that most of the Mediterranean has a dark blue color, which means that it's very poor in phytoplankton, very poor in anorganic suspended matter. Only if we close to the surface, if we are close to the coast, then we can see that there is this line, these areas where the color becomes more greenish. And this is the area where the fresh water coming from the land, rich in anorganic material and in phytoplankton, flows along the coast towards south. So, if you remember, we were discussing this, what kind of information you can obtain by looking simply at the satellite data. Obviously, these are the qualitative information, non-quantitative information, but you can learn a lot of how your ocean functions. Here is you can see also here this white stuff. These are this is the snow at the Alpine mountains, and here these are the clouds. So you can see that you can obtain number of information, or the snow coverage, or the clouds, and so forth. Not only information on what is going on in the ocean. Here is another interesting satellite image. This satellite image shows not only what is going on in the ocean, but shows also what is going on in the atmosphere above the ocean. What you can see here, we can see here is that this huge yellowish, brownish area here, which is not associated to the wind, to the sea. It's associated to the state of the atmosphere, to the dust presence in the atmosphere. So you see how the atmosphere is in between the ocean and the atmosphere, and it influences what is going on. So you have to know a little bit on what is going in the atmosphere before interpreting what you can see from the satellite data. And so once one wants to see, but where these dust comes from. So if you go and look at the meteorological conditions in this specific situation, which is, I don't know exactly which dates, the wind field over the Mediterranean was that there is a strong southeasterly wind. So the wind blowing from here toward the Adriatic. So the wind blowing from the African coast means that this wind takes with it the Saharan dust. This Saharan dust is transported over large distances. You can see that these are the order of 1,000 kilometers. Is transported from Africa into the large part of the Mediterranean, including also parts of the Adriatic. In fact, in some situation, when there is a strong southeasterly wind, if you leave your car outside, it will become yellow due to this Saharan dust transported from African coast, African deserts. And here is another nice picture showing, and here is much better showing where this Saharan dust comes from. You can see that's the plume of the Saharan dust originating from the Sahara, from the African desert, and being transported into the entire central Mediterranean. Okay, there are some clouds here you can see, because typically what is happening is that southeast wind is associated to the low atmospheric pressure here, and to the rainy weather and high tide in the Venice Lagoon. But another phenomenon which is associated to this thing is also the event of the arrival of this large quantity of Saharan dust into the area. There is another interesting thing, but I won't talk to you about too much about this. Saharan dust is very useful for reaching the sea by nitrates, by the material which is used by phytoplankton. So typically after these kind of events, you can have also the strong phytoplankton bloom. But this is something which is doesn't make part of this course. Ocean color, okay. And here is how do we use the ocean color data. And so as here you can see that this is the sunlight, okay, and about 40% of this sun energy is absorbed by Earth's surface. A small amount is reflected back to the atmosphere, and about 20% of the absorbed directly into clouds and other components such as ozone and carbon dioxide. So one part of this, which is reflected into the space, only one part then can reach the satellite and can be used to study the ocean color. And there is another complication of the system, that about 40% of the energy coming from sun is reflected by clouds. So very little part of this energy which comes from the sun is reflected to the satellite and can be used to get the information on the satellite, on the sea surface color. Not only sea surface color, because what is going on is that the sun, which transmits the energy at the sea surface in a visible part of the spectrum, this can enters into the sea and is absorbed in the first part of the first layer of the ocean, which we call photic zone. Photic zone is the part of the ocean where the light reaches the depth to which the light reaches the ocean. Photic zone is very important because that means that all the organisms which are living there, which needs the light to live, they are concentrated, all of them, in this photic zone. And this photic zone is about 100 meters deep. Therefore, by getting the information on the ocean color, we obtain the information also on the photic zone, on the presence of the concentration of the phytoplankton in this specific zone. So let's see. These are the spectrum, and this is where what we really look at the backscattered sunlight in order to obtain the information on the ocean color. We have a number of clean ocean water as a maximum backscatter in a short blue wavelength, which is this thing here, and almost zero in yellow and red. So if you have the clean ocean water, it's blue because mainly has a maximum backscatter in the short blue type of the spectrum. Higher these phytoplankton, chlorophyll and other plant pigments concentration, and more is the contribution of green color. So the green color becomes more and more important, relatively more important, because here is you can see the blue, ocean, the clean ocean is this thing here, and then relatively is more important green or even the red part of the spectrum when there is when there is a strong high phytoplankton concentration. So this part here is due to the presence of the phytoplankton. In a coastal zone, on the other hand, which are characterized by the high concentration of anorganic and organic matter. Organic matter is the dead animals, dead plants. The reddish part of the spectrum becomes larger than any other part, with respect to obviously to blue and green part. So this is how do we explain the different colors of the world ocean, and how do we then can we by looking at the differences between the blue and green spectrum, we can calculate the concentration of the phytoplankton by doing the validation, obviously by doing the validation of the in situ data by the data measured in situ from platform and so forth. Here are the what I think we have seen. This thing here is the phytoplankton pigment or chlorophyll concentration at the Earth's surface. which is the long-term average. And what is clear, and what we have also mentioned before, but it's nice to repeat this, is that essentially there are two belts of the low concentration of chlorophyll in subtropical areas, where the low concentration is due to one thing which is important to remember. You remember that these areas here is the areas of the subtropical gyres. Subtropical gyres to the north and south are the areas where we have the convergence, and the convergence means that you have the downward flow at the surface of these gyres, at the center of these gyres, which means that the concentration of the chlorophyll is very weak, and the production, or primary production, we call it primary production, the phytoplankton biomass, and its production is very low in these subtropical gyre areas. Repeating the old concept, in the areas where there is equatorial convergence, we have the really higher concentration of the phytoplankton, and which is due to the divergence. So we have the upwelling, and having the upwelling, we have the higher concentration of chlorophyll in the equatorial areas. There are a number of other interesting things what can be seen. Just to remind you that the areas where the primary production of biological production is very low in the subtropical areas, the extension of these areas in the continents are the desert areas. So here, this is the African desert, and this is the North African desert, this is South African desert, this is the American desert. So the desert areas is really at the same latitude as the desert areas in the ocean, because of the specific climatic conditions, but not only because of the convergence or divergence. Some smaller scale structures can also be seen from these images. For example, this reddish area here along the South American coast. Here is more or less, here is the Amazon River, and Amazon River water goes along the coast and extends in this area here. And if you remember this thing here, if you have dead organic and inorganic matter, that the red part of the spectrum becomes predominant. Therefore, this is the sign of the presence of the river water, which extends along the coast. And we know all the Amazon River is one of the largest rivers of the world. Here, along the South America, but on the other side, we have the yellowish area. Yellowish area is the high concentration of chlorophyll due to the upwelling, due to the coastal upwelling, which we have been talking to you before, and you will be discussing a lot about that connected to the El Nino phenomenon. Okay. There is one passive sensor which is now in development, which is the sea surface salinity from satellite. So we are able not only to measure sea surface temperature, but we are able to measure sea surface salinity. We will see later about sea surface salinity temperature. Now, just to give you an idea that the sea surface salinity is another very important parameter which can be measured by the remote sensing method, and it reflects again what is happening in the world ocean. Again, the high sea surface salinity in subtropical areas, and both in the Atlantic and in the Pacific. So essentially, the same pattern is obtained from these data, from salinity distribution as well as from temperature. Ocean color, as I told you before, can be used also as an indicator of what kind of dynamical or kinematical properties of the ocean are present. It's enough that we have high gradients of the surface chlorophyll concentration. So this is for one example of this. This thing is the area of Gulf Stream. The area of Gulf Stream is that in the coastal area is rich in not only in a phytoplankton, but it's rich also in inorganic and organic material. And you can see the front. This is the front. So the strong changes of the oceanographic properties crossing these area here. And so this is the front associated to the Gulf Stream, because the Gulf Stream is flowing northward and taking the warmer water from south to the north. But it's not only that that water has thermal characteristics, specific thermal characteristics. That water has also specific biological characteristics, which are clearly explained here by these frontal area, where you on one side you have the open ocean and poor in chlorophyll, and on the other side you have the other part of the ocean which is rich in chlorophyll. Another very interesting is that how the ocean color can determine or the presence of the smaller scale structure, what we call mesoscale. These are the warm core rings or cold core rings. These are the closed structure which are present associated to the Gulf Stream, which are for the longest front. This is one front, and they are front, and then travel by itself. And they are the fronts. They are rings which are poor in chlorophyll, as the same as the open ocean. And they travel, and they are on their spatial scales are on the order of 300-400 kilometers. They have lifetime on the order of a year or two, and they take the characteristics of the open ocean water into the area which is rich in phytoplankton. So you can see how many information you can obtain by simply looking the ocean color. The same or similar thing you can obtain and confirm from the sea surface temperature distribution. Another example is the African coast. This is Madagascar, and these are the two situations. One situation is in a monsoon. This is the monsoon situation, and this is non-monsoon situation. When there is a monsoon, the wind is blowing this way and creating the coastal upwelling. The coastal upwelling means that you have bringing the nutrient-rich waters into the surface and increasing the concentration of phytoplankton or phytoplankton biomass, which then changes the color of the ocean and which becomes the yellowish or even the reddish. So this huge area of the reddish or yellowish is due to the coastal upwelling generated by the monsoon, which is absent obviously when there is outside of monsoon season. Okay, so these are the scale is phytoplankton pigment concentration. It's in milligram per meter cubic. And so that's how we use these data, not only to study the phytoplankton lifetime, but we use this data also to interpret the oceanographic features. The ocean color can be also seen very nicely in the Adriatic, and here is a very interesting picture where there's a combination of chlorophyll concentration, which are these background colors from reddish or brownish to bluish, and superimposed on that are the chlorophyll, the drifter trajectory. What you can see is that the drifter trajectory follows are nicely put along the fronts, along the area which separates the coastal area, rich in phytoplankton, rich in dead inorganic material, from the open sea, which are again fronts, the similar fronts as we have seen in case of the Gulf Stream. And these fronts or the current is flowing southward, and which is nicely seen from these drifters which are flowing this way. If you are looking at the open sea, they are not, the trajectories are less organized because there is no definite prevalent current southward as it is along the coast. Here is another example. Again, confirms the same thing. You can see these currents flowing southward, less organized open sea currents. Again, this thing here. You can see also that there are some smaller scale structures, closed structures, which are appearing along. And here you can see that how these drifters entered into the coastal current and flow southward. Now we have let's move to the sea surface temperature measurements, which is this satellite, what is NOAA satellite, is advanced very high resolution radiometer, and this measuring the spectrum, and then this algorithm here that is used to estimate the SST from these peaks, which are in the infrared part of the spectrum. So this is the how from the received signal, because this is the passive satellite. It's using the algorithm is estimating the SST. It's important again that that we have to take into consideration that the clouds represents the noise to the measurements of the sea surface temperature, because they have their own transmission, and the transmitted signal from the satellite, from the clouds has to be removed from the received signal from the sea surface temperature. Here is the antenna. What we have here, the antenna which receives the signal from satellite, which are then analyzed using these algorithm, and then we obtain the sea surface temperature every time when the satellite passes over the antenna. Here is an example how this looks like. You can see that there are now a huge number of zones which are covered by clouds. All these black zones are cloud covered, and it depends also. If you do your measurements during the summertime, obviously your coverage will be much better than during the winter time. So this introduces certain bias into the statistical value of the sea surface temperature, because from the statistical point of view, the sea surface temperature in summer will be much more significant than in the winter time, because we will be having much more situation of this type where the presence of clouds doesn't allow us to measure the sea surface temperature. Okay, so this is the comparison between the composite SST image. SS composite is because we cannot, because of this poor coverage of the ocean due to presence of clouds. We cannot have a single image because there is the presence of clouds. We do have to use the composite SST image in order to reconstruct as much as possible the good coverage, spatial coverage with SST measurement. And here we have put together what has been measured from ocean color and from the sea surface temperature. And you can see that these eddies or rings which are present here, they are also here. You see that? So there are number of mesoscale structures which can be seen both in temperature and in chlorophyll. It's enough, as I told you, it's enough that there is a strong gradient between one area and the other. And indeed, here is a strong gradient between the open sea in the chlorophyll concentration in the coastal areas, as it is the strong temperature gradient between the open sea, where there is a higher temperature, which is taken by due to the heat transport area, which is very cold, but at the same time is very rich in chlorophyll. Cold areas are very rich in chlorophyll, while the open sea, rich, relatively warm areas are poor in chlorophyll. So you can see that more or less this reddish part in the temperature corresponds to the bluish part in a chlorophyll distribution. Here is something. Here is the global Earth global surface temperatures in 2019, and compared with the difference between 2015 and 2019, and you can see how what we can do with using these global Earth temperature measurements. We can compare and see how locally or regionally the temperature changes between different parts of different periods. And what is evident from here that that most of the Earth's surface is warmer in 2019 than in 2015, except some isolated areas along the Antarctica or the Greenland area. So you see what enables us to study the spatial and regional variability of currents in studying the temperature, in studying doing the climatic studies. So that's some. The only problem with these satellite data is that unfortunately they start early satellite sea surface temperature measurements have started in the 80s, so only 30, 40 years of data, and in order to obtain some important information on the long-term climate variability, we have to have much longer series. Remember that the climate, or with respect to whether we define the climate, is meteorological conditions over the period of about 30 to 40 years. So we are not enough even to define very well the climatic conditions from using the satellite data, and not talking about the long-term climatic changes. Here is the temperature anomaly, what we have seen before. So now we are in altimetry. We have the altimetry, which is an active sensor, where the satellite sends the signal to the surface, and then looks the time. This is microwave measurement, and it sends the signal to the surface and looks the reflected signal and measures the time needed to the passage, the different time difference between the time the signal reaches the surface and coming back. And so this is and it measures whatever is, it measures the structure of the sea surface, which depends on the geoid. You remember when we have defined the geoid. We define the seafloor topography, where seafloor topography then determines the deformation of the sea surface because of the different mass between the sea surface. Therefore, we can study seafloor topography using the altimetry. So the altimetry is really very very useful studies. And here is what I showed you before. How the seafloor impacts the sea surface pattern, so that we can looking at studying by altimetry, studying the sea surface pattern, we can study the seafloor structure. Here is the altimetry what I already showed to you. Here is another example, and here is some, to give you an idea, what do we really, what kind of study we do by doing the satellite measurements of sea level changes. We do measurements of the thermal expansion, of the increase of the temperature, which then reflects in the thermal expansion of the sea. We have the melting of ice due to which there is a sea surface height increase. Okay, we have and since the ice is the melting, therefore the pressure of the ice to the Earth surface is decreasing, and therefore we have a rebound of the land and increase of the Earth. So this is what we do with the satellite measurements of the sea level changes. We obviously use also the island tide gauges, and these island tide gauges are used to see if you want to analyze the sea level changes on long-term time scale. We have to eliminate the tides. And how do we eliminate the tides? There are two ways. One is certainly using the island or coastal tide gauges, so the instruments which are fixed at the coast, which are relatively few of them along on the Earth's surface. And the other thing is to use numerical models. So we using the island tide gauge or fixed tide gauge at the Earth's surface. Then we run the numerical model. We determine the tides. We calculate tides for each specific point of the ocean, and then subtract these tidal signal from the thing what is measured by the satellite, and then we obtain the pure non-tidal changes of the sea level. And this is what we used really for determining the climate, the sea level change. Okay. Satellite altimetry, as I told you before, is used also to measure the marine geostrophic currents, simply because simply using the relationship for the geostrophic balance, which says that the surface geostrophic current is proportional. G is gravity constant, F is the Coriolis parameter, and d theta dt is the horizontal gradient of sea surface height. So we, at each point, from the satellite measurements, we can determine the velocity, and we obtain the geostrophic wind velocity, geostrophic current velocities all over the world ocean by simply doing the sea surface height measurement. So therefore, we have not only that we measure the sea surface height, but we do measure also the surface geostrophic flow. And as we have seen before, that the surface approximation, the geostrophic approximation, is a very good approximation for long time and spatial scales in the world ocean. I showed you before how fits very well the measurements by drifters with just marine geostrophic currents obtained from satellite measurements. Here is the pattern. Let's see, and here is this is the for example, this is the long-term trend of the sea level for European seas, and this is that's another this is the important information that we get from these measurements, that this is for the period 1992 2011, so it's only 19 years, but already in that relatively restricted range of time range, we can see how heterogeneous is the trend in absolute sea level across Europe. You can see that there are areas which are reddish. That means that the sea level height is increasing. There are areas where the sea level height is decreasing. In the Atlantic, the sea level rise is stronger than in most part of the Mediterranean. These small-scale structures, probably they reflect what is happening as a circulation in the ocean, which then influence the variability on the atmosphere. So that's here is the combination of the main near surface current and sea surface topography. Sea surface topography for a larger period of time with superimposed geostrophic flow, geostrophic current pattern. And what you can see here is that the reddish area here is the higher sea level than the bluish area here. The geostrophic flow leaves the high sea level on its right. Therefore, we already know by knowing the geostrophic balance equation that the flow is flowing this way, eastward, and doing these series of meanders, flowing eastward, and then doing the whole tour around the easternmost part of the Mediterranean and going back into the Western Mediterranean. And you can see that there are not only these basin scale flow, which is present also here, but there is also certain number of mesoscale structures which are cyclonic or anti-cyclonic, clockwise or anti-clockwise, which are more or less permanent. They have even their names because they're almost always there. They are not like in a case of the Gulf Stream, which you have these rings which detach from the main current and then flow, and then after 2-3 years they just die down. Here, in this case, you have a semi-permanent structures which are present always there, and so they are clearly evident from the altimetric measurements. Absolute altimetric sea level averaged over a period of 1 year, over 6 months. Here you can see here. What you can see from here is and so this reddish line is the trajectory of a drifter, which has been deployed here, and you can see that it did some trajectories here in this area here, and then entered into the southward flowing stream, and then finally you can see eventually exits the Adriatic, and doing some small scale structures. You can see these small scale structures, and end up even you see how long track he did. If he superimposed on that absolute altimetric sea level average over that period where the drifter was launched until the moment when it died down, you can see that how this fits very well. The drifters follow very nicely these strong current, southward current, again leaving the high sea level on its right, and flowing these all the time down, and so that's the so you can see here how Lagrangian current measurements obtained from trajectories of co-drifters, how they fit very well from the altimetric data for obtained from satellite. Take into consideration all the time that here altimetric data has been averaged over 6 months, averaged long enough in order to reflect the geostrophic balance, the geostrophic currents. Okay, so this is the sea surface height again. El Nino and La Nina, you will hear a lot about these things in the next lectures. The only thing what I wanted to tell you is that you can see that differences between El Nino and La Nina can be seen from the sea surface height. The higher is the sea surface height, the warmer is the sea. So and vice versa. The lower is the temperature, is the lower is the sea, because of this variability of the volume of water due to the heating or cooling. So the signal of El Nino or La Nina, these kind of structures, can be also studied using the satellite altimetry to monitor these the characteristics of the climate. Global warming, sea level rise, I already showed it to you. Another, as I mentioned to you, another important parameter which is not directly associated to oceanography but has an important oceanographic aspect is the wind measurements. Wind measurements before, they have been done only on single points or means a very spatial resolution. Remote wind, can you hear me? Okay. These remote wind measurements they are much more limited over the land, and is primarily obtained by anemometers located in small islands. Weather stations, so there are weather stations. I mentioned before to you that there used to be weather stations in the northern Atlantic, where about 10 weather ships were moored there, and they were measuring all the oceanographic and meteorological parameters, which was very extremely expensive. And so, since the ocean regions are large, especially the Pacific, the knowledge of the wind characteristics of this area is important to weather forecast, ocean navigation, and climate studies. For example, to give you an idea, the climate or meteorological conditions over the Europe is mainly dictated what's happening in the northern Atlantic. So what that means? That means that if you want to have a good weather prediction in Europe, we have to have a very good and very fine measurements of the wind over the North Atlantic. And in fact, that's why all the ships, these 10 ships, were located in that area of the North Atlantic in order to obtain the meteorological information which then were used to do the weather forecasting. So, but that's the question of the Atlantic. We have the same problem of Pacific, even bigger, because the Pacific is larger ocean. So, you can see here that one of the first approaches was to use visible images to study cloud movement and indirectly determine the wind speed and direction. And this method is still in use today, but now the wind measurements are using the scatterometer, which sends the signal from the satellite, sends the signal to the Earth surface, which then reflects off by the Bragg waves, and these are wind waves, ripples on capillary waves, which are superimposed on these large wind waves. So this reflected energy is then measured by scatterometer and translated into 10-meter neutral wind speed and direction. Because these small capillary waves, their progression, their changes, they are determined by the wind over the sea surface. And so the special processing technique, we obtain wind speed and direction every 12 kilometers over the ocean. Can you imagine what is the huge progress in weather prediction when these remote sensing wind measurements has been included in the information of these wind measurements has been included into the numerical models. Here is this is one thing. So one aspect is to obtain the information on which are then used to do the weather prediction. There is another very important aspect of these scatterometer wind measurements is that it gives the very high spatial resolution on the order of 12 kilometers, which then gives us the possibility to all the small scale in the atmosphere, because the atmosphere has large structures which are mesoscale cyclones and anticyclones, which are on the order of 1,000 kilometers. There is no problem about resolving them, or even with the classical measurements. But if we are talking about the tropical cyclones, which are on the order of tens of kilometers, or if we are talking about subtropical cyclones, which are can you hear me? I can see only every now and then I can see that the connection is not stable, but maybe it's a wrong. Anyhow, so these quasi-tropical cyclones, which is here an example, which is a year ago, and this is formed over the Mediterranean. This is Italy. You can see Italy. That's Greece here. It has been formed someplace here south of Sicily, and then traveled toward east. And you can see how perfectly they're resolved by these scatterometer measurements, and you can see the velocity, which is much stronger in these small scale structures than over the air. And you can see from one hour to another hour how it progresses eastward. And so that's a very important aspect of using on these scatterometer wind measurements. We have also try to compare the we also try to compare the measurements by the we compare also the measurements obtained from coastal radar, from scatterometer data, and from the numerical model of surface current. So we have three things. We have the wind, which is the forcing. We have the measurements by HF radar, which is the response of the surface current to this wind. And we have the numerical model, which is, sorry, this is not the numerical model. These are the geostrophic currents obtained from the altimetry data. And here you can see obviously here you don't see the wind data, because the resolution of the wind is larger than this. Here we have a very high resolution on the order of a kilometer, and more or less similar to the resolution by geostrophic calculations. And you can see how they fit very well one to another, HF radar and altimetric geostrophic currents. This is one interesting figure we shows. On one hand, this is the HF radar. Here is the geostrophic current, these reddish arrows, and these black arrows, these are the wind. So you can see that still there is a pretty high differences in the horizontal resolution between the wind and meteorological measurements and oceanographic measurements, but at least you can get the idea of what is the direction and speed of the wind on much higher resolution. And so here is, for example, the zooming of this picture. We zoom on that, and here is the geostrophic currents. The blue arrow is the wind, and this is these are the radar measurements. So you can see that when there is a strong wind blowing in that direction, it generates the surface current, both and which is reflected both in geostrophic currents and in the radar measurements. But one can ask you, well, but if I'm talking about the geostrophic currents, but geostrophic currents are in equilibrium, therefore there is no outside forcing. How come then the wind direction fits very well with my geostrophic current measurements? Because what is going on? It's going on that the wind generates the sea surface slope, and this sea surface slope then is reflected in a formation of the geostrophic currents. So this is the evolution of the flow field, and combination of high frequency surface geostrophic flow and the high frequency, high resolution scatterometer data. Here is, you can see this, here is the 10 meters per second is the velocity of the wind, 1 meter per second, and 1 meter per second is the velocity of the surface current. These measurements are also reflects also the small scale structures. The geostrophic flow and the HF radar can be seen very, they fit very well one to another, and they are associated to the wind, which probably generates this kind of eddy. Now here is another interesting thing. Here we have combined HF radar surface flow and chlorophyll distribution. So we are now trying to combine all these information that we obtain by, and obviously also here is the wind. You can see that's the wind. That's the wind data. Here we combine all these measurements in order to obtain the most complete information on oceanographic pattern, on oceanographic situation. Because as I told you before, we can look simply also at the chlorophyll distribution, which is this background reddish or bluish colors, which will give us the idea what is the circulation. But if we combine this directly with the surface current measurement, in that case we have a confirmation that whatever pattern we see in the chlorophyll is reflected by the horizontal circulation. Here is similar thing, just to give you an idea. Here we can see some evolution of thermal structure in the Mediterranean. Just to illustrate to you the composite satellite images. Here is the satellite images composite between A1 and A January, as I told you. In order to obtain as much information as possible, we have to do the composite satellite images. And but still, you can see that still a lot of black areas remain due to the presence of the clouds. And here, essentially, you can see the known pattern what we have already studied. This is the chlorophyll. I told you the chlorophyll. That's the chlorophyll. And so you can see that the northern areas are usually more rich in suspended matter, except this area here, which is very shallow area, which is a lot of suspended matter. Open sea Mediterranean area, especially eastern part, is very poor in phytoplankton and suspended matter. Therefore, is very blue with respect to blue color with respect to the Western Mediterranean. From 9 to 16 January, you see this is 9 to 16. You can see that the situation changes, but essentially the structure or overall pattern remains as it is, where the open ocean is poor in a chlorophyll, and the north, the Western Mediterranean is much richer in chlorophyll than the Eastern Mediterranean. There are some changes on the smaller scale structures, which are due to the vertical convection or are due to the strong shelf of fresh water from the coastal areas. Here is the 10 to 17 February. Again, you see that the pattern looks more like a previous one. And here is the 26th to 7th February. Here now the situation has changed, at least from the small scale structure. These things which used to be bluish now becomes brownish because of the formation of dense water and the vertical mixing, which then brings increases the primary productivity in the surface area. And this is the clear signal of that thing here. Here is another area of the dense water formation, which is the far eastern part of the Mediterranean. And again, here you can see this brownish patch. I repeat, in order to interpret these things, you have to know the oceanography of the area. You cannot, otherwise you cannot interpret this. Here is another area of dense water formation, which is Gulf of Lions, where this vertical place. And here is always March. Here is practically there is no patch. Here patch still remains. Here is the patch, which is very strong. And the large scale structure, you can see they remain more or less maintained as it was. So there are changes on a small scale structure, but the large scale structure, and overall structure is more or less good, present there. Here is how it looked like, the evolution, and here is we are at the end. So I hope you were able to follow this. I hope it was useful. I hope this. The thing is that this part of the course will be very good introduction for this coming next, in the sense that the next part of the course will have an important formal part of mathematical development of these concepts. Therefore, but I would like to ask you to keep in mind all the time the physics of the process, because the mathematical formalism is simply a way to describe in a very economic way the processes in the ocean. But in any moment, when you look at the formula, you have what it means from a physical point of view. And that's important. If we are talking about the geostrophic currents, we know that what is the expression of the geostrophic currents, but you have to know what that means in terms of the physics of the ocean. You have to know that geostrophic approximation cannot be applied on a time scale on a day. You have to know that on a longer time scale, this geostrophic approximation can be approximated. On a long time scale and a large spatial scale. And you have to know, for example, when you are talking about the wind influence, that this is another example where we obtained a simple mathematical analytical solution, which then describes very well what is going on in the ocean, but on a long time scale again. Or when you will be talking a lot about vorticity, about the stretching and the squeezing of the water column. You will be talking about the various wave solutions of the equations of motion, which includes the vorticity conservation, potential vorticity conservation. And this, in that case, you always have to have in mind, in front of you, you have to have in mind the physics of the phenomena. Okay, so this is a unique course. It's not there are no three courses. It's a unique course which simply tries to give you an approach from different point of view, which then you have to integrate that and try to extract as many information as possible and go on with this. Okay, so I'll give you 5 minutes earlier. Since you are trying to, you know what is the problem with PowerPoint? I admit you, I think I didn't have any problem with you in sharing with you because you have the Gmail, and I don't know whether everybody has a Gmail address. Because when I have to share with somebody who has a Gmail address, in that case, it accepts me sharing it immediately. But I will retry and I will try to resolve the problem. This is a technical problem. Okay. So have a good time and enjoy the rest of the course. Enjoy the nice weather and see you around.
Thank you.
Thank you. Bye.
Bye-bye.
Thank you so much.
Bye.
Bye. Thank you. Bye.